This is the screencast for section 8.3, example 5. Now, transitivity of growing rates. If you remember the transitive property, it kind of means it can be passed along. So if f grows at the same rate as g as x approaches infinity, and g grows the same rate as h as x approaches infinity, then f grows at the same rate as h as x approaches infinity by the transitivity of growing rates. So if f is to g and g is to h, f is to h. And our general strategy will look like this. The limit as x approaches infinity of f over g will be constant. The limit as x approaches infinity of g over h will also be constant. So then the limit of f over h, the numerator over denominator, will equal f over g times g over h. So L times m. So example 5 says, show that f of x equals the square root of x squared plus 5 and g of x equals that. Grow at the same rate as x approaches infinity. Well, if I notice, this has a square root of x squared in it, and this has a square root of x that is being squared, so technically both have x to the first in there, sort of, so I kind of know they should be growing at the same rate. Plus it says show that it does, so it does mean that it does. But if I just take the limit as x approaches infinity of f over g, yikes, that is a horrible, horrible quotient to deal with, and L'Hopital's rule would get messy. So instead, let's take the limit as x approaches infinity of f over x, and the limit as x approaches infinity of, now I know it's supposed to be x over g then, but trust me, I fixed this later. I just think it's easier to make the binomial in the numerator for simplification purposes. Alright, so hang in there on that. First, looking at this side, well, right now I'm getting infinity over infinity, so instead I'm going to take L'Hopital's rule, derivative of the numerator over derivative of the denominator. However, now I'm getting infinity times infinity in the numerator, so that just made it even messier. So, or even if I distribute the 2x, I'd get infinity plus infinity. That's not good. So let's start over. And instead of using L'Hopital's, let's do a little bit of simplification. So let's take that x and change it to the square root of x squared, which still means x, but now I can combine some things. So now the square root of x squared over the square root of x squared is 1, and then the square root of 5 over the square root of x squared is 5 over x squared. So now I look at this as x approaches infinity, I have the square root of 1 plus 0, which is 1. So I've got a constant for f over g. Now let's try h over g, or well, in our case, f over x versus g over x. I get infinity over infinity again in the first shot here. So if I use L'Hopital's, take the derivative of the numerator, derivative of the denominator, same thing. I get infinity times infinity, too messy. Let's instead work towards simplification. And by too messy, I mean that L'Hopital's only really works with infinity over infinity or 0 over 0. So this shows evidence it's not working. It's actually making it into a indeterminate form that we would have to work at to get it to be infinity over infinity. So we're kind of going this cyclical bad pattern here. Alright, so now I changed the x to square root of x squared. So now I can combine the stuff inside the parentheses because they both have the same exponent. And 2 square root x over square root of x is 2, and then 1 over minus 1 over square root of x squared. That's a little bit easier to work with. I get 2 minus 0 squared, which is 4. Again, a constant. So, the limit as x approaches infinity of the square root of x squared plus 5 all over 2 square root x minus 1 quantity squared. So this is f over g, what we're trying to find. That can be rewritten as the limit as x approaches infinity of f over x times x over g. Now those x's would simplify and you'd get f over g, the original that I'm trying to find. So here's where I told you I would fix this problem. Basically, the limit as x approaches infinity we found is 1. The limit as x approaches infinity of this, I would have to take the reciprocal and use then 1/4. But it was easier to put the binomial in the numerator because then you could simplify. So now I get 1/4, which is a constant. Therefore, f of x and g of x are growing at the same rate. So now try problem number 31. We're going to look at a different strategy for making the conclusion that these two are growing at the same rate. We're actually showing that the three functions grow at the same rate as x approaches infinity here. Yikes. Okay, so first I'm going to use that same transitive property, and I'm going to pick f of 1 to compare f sub 2 and f sub 3 with. Now the reason I picked f sub 1 is because f sub 1 is a simple square root x, which is going to be easy to simplify with f sub 2 and f sub 3. If I put f sub 2 and f sub 3 in a rational expression, yikes, that's really messy right there, so I'm not going to do that. So I'm going to use the limit as x approaches infinity of f sub 2 over f sub 1 and the limit as x approaches infinity of f sub 3 over f sub 1. Again, using the strategy of the binomial in the numerator. Now, f sub 2 over f sub 1 gets plugged in. Now I can simplify. Square root of 10x over square root of x is just 10, and then I have 1 over x inside, all inside that square root, which has a limit then of square root 10. Now this side, over here, plug in f sub 3 and f sub 1, same strategy, I'm going to simplify, and that limit is 1. So now I've shown that f2 and f1 grow at the same rate as x approaches infinity. I've shown that f1 and f3 grow at the same rate as x approaches infinity. Therefore, by the transitive property, f2 and f3 grow at the same rate. So all three functions grow at the same rate as x approaches infinity. So this one I had to state the transitive property because I was using all three functions. The previous problem, I used the transitive property, but I showed that only two functions grew at the same rate by making up a third one on my own. So I didn't have to use that third function in my final conclusion. I just showed that the comparison between those two was constant.